He's advised by Guy Blalock. His main interests are in parallel graph algorithms and graph processing systems. So his paper is one of our best paper awards. Okay, let's welcome him.
Great. Hi, everyone. Thanks very much for coming to the last session today. I know you probably all want to be somewhere else, but thanks for being here. Today I'm going to tell you about our work on low latency graph streaming using compressed purely functional trees. Everything I say is joint work with my advisor Guy Blalock and Julian Shun from MIT. So real-world graphs are dynamic, and many graphs that you actually derive from real-world data actually change over time. This stands in contrast to most graph processing systems out there today, which are static. And you lose something when you take a truly dynamically evolving graph and represent it using a static graph system. You basically lose all of the properties of how this graph is evolving over time. And so it's an important research question over the coming decades to actually design systems that can represent and mine information about the dynamic nature of graphs. In addition to being dynamic, real-world graphs are also massive. And many graphs out there today have billions of edges to hundreds of billions of edges. In fact, the largest publicly available graph, the Hyperlink 2012 graph, has close to 4 billion vertices and 225 billion edges. And there are larger graphs out there today at private internet companies. As I mentioned, the largest publicly available graph data set has over 200 billion edges. And if you look at their website, they say that this is essentially the largest graph that's out there today that's not at one of these private tech companies. Even in the static setting, processing a graph at this scale is a challenging task. And most people in the literature up till very recently have been using distributed graph processing systems, often getting running times with, on the order of minutes to hours to mine analytics from these graphs. In recent work with my co-authors Guy and Julian, we showed in SPA 2018 that we can actually represent and efficiently solve problems on a graph at this scale on a single multi-core machine. So on a single machine with a terabyte of RAM, we solved a list of 15 fundamental graph problems. And we made the implementations that were used as part of this work publicly available, and you can find them on GitHub at the link at the bottom of the slide. One question that we left unaddressed from that work is the case when the graph is dynamic. And so a very interesting open question is whether we can design a graph streaming system or a dynamic graph processing system that can efficiently represent and process a graph like the Hyperlink 2012 graph or other graphs at this scale. Now, I want to tell you a little bit about the graph streaming model. This is a kind of informal model that people have been using in the literature to study dynamic graph processing systems. In a graph streaming model, we have a graph G that's undergoing edge updates or vertex updates, and these updates are arriving online in a stream. And so you can think about this as the real world basically telling you what changes have occurred to this graph. And the updates stream can either be batched or unbatched. In this paper, we assume that the updates are batched because it's an interesting question given a stream of updates to figure out what granularity you want to batch it at. And it's not a question that we address in this work. In addition to the updates, there's a stream of queries that are being executed by users who want to know some property about the graph. And these queries are arriving concurrently with the updates. So a user might be interested in, for example, a local graph algorithm. Like, for example, a very trivial one would be finding the degrees or the number of two-hop neighbors at a vertex, or the local clustering coefficient at a vertex. And also global graph algorithms, like computing the connected components, or generating a clustering of the graph at a recent point in time. And the goal for a graph streaming system is to achieve serializability for both the updates and queries. This is the gold standard that we're shooting for, and to achieve both low latency and high throughput for the updates and the queries. So the queries should basically behave similarly to how they would perform on a static graph processing system, and the updates should be applied in near real time and made visible to any new queries that arrive online. Are there any questions about the model? I'll go on. I guess we'll take questions at the end. So as an example of the graph streaming model, I want to motivate it with one particular example, which is fraud detection. Here you might be working at a bank and you have a transaction graph. The graph could have both finished transactions and pending transactions, and these are occurring at some high rate between 1,000 to 10,000 transactions per second. And the goal of the bank is to detect in nearly real time some anomalous patterns in this graph. So it wants to detect fraud and squash it as quickly as possible. So one example of an anomalous pattern might be a directed cycle, like a directed triangle. And so in this graph, we might want to detect this red triangle very quickly in near real time and mark these transactions as bad and not let them occur. And so you can imagine people at banks have a big vested interest in actually designing systems that can do this in near real time. I mentioned that this is not a new problem that we're studying. There's many papers out there that propose essentially to build a single version system. As the name suggests, in a single version system, you maintain a single version of the graph, and you share this between the updates and the queries. So when updates arrive, they take a lock on this data structure, on the version, apply themselves, and then release the lock. And similarly, when queries arrive, the queries take an exclusive lock on the data structure and run. However, this is an issue because now the updates and queries are blocking each other. And if my updates are arriving at a very high rate, they're going to starve the queries. And similarly, if I had some long-running queries, they starve the updates. And furthermore, if you have a long-running query, it makes the graph stale for any short-running queries that arrive after it. And so it's an interesting question whether you could run these updates and queries concurrently. Now, people have thought about whether you really need serializability, because the prior slide is only true if you really want to guarantee serializability, but bad things start happening if you get rid of serializability. In particular, if you think about the fraud example, the moment you get rid of serializability, you can start detecting objects that never existed at any point in time in the graph. So you might find a directed triangle when in fact that directed triangle never existed. It might be some proposed transaction that was then deleted. And so, for example, if you're trying to buy a gift for your mom for Mother's Day, or maybe for Father's Day for your dad, and your transaction was marked as faulty, you might be kind of annoyed. And so this lack of serializability in the system would translate to some user-facing issue, and the bank definitely does not want to do this. So guaranteeing serializability is an important kind of property for real-world systems. People have also thought about this, and there have been some proposals to design systems that can both guarantee serializability and concurrently process updates and queries. And so these systems are based on supporting multiple graph snapshots, like Llama and Kineograph. However, both of these systems suffer from a high space inefficiency, and because they are unable to generate low space snapshots, this leads to very high latency. So when you process a small number of updates, you incur a very large latency before these updates are made visible in the graph. So it's an interesting question, given the state of affairs, whether we can actually design a graph streaming system that's able to represent, analyze, and update the Hyperlink 2012 graph, and also similar graphs at this scale, with very low latency for both updates and queries on a single multi-core machine. And in this work, we design a graph streaming system called Aspen, which solves this problem. Aspen is a graph streaming framework that extends the Ligra graph processing framework from PPOP 2013. Aspen supports serializable updates and queries with very low latency. So when you're running the updates with a single update at a time, you can make these updates visible with microsecond level latency. And it also extends to processing batches of updates in parallel with very high throughputs up to the hundreds of millions of edges per second. In terms of space usage, Aspen gets up to a 10x improvement over the space usage of existing systems. And the key idea in our work is to use a data structure that we designed called a compressed purely functional tree to improve both the space usage and locality of our graph snapshots. And as one experimental result to take away, it's that Aspen can concurrently apply updates and run analytics both at the same time on the Hyperlink 2012 graph using 1 terabyte of RAM on a single multi-core machine. So I'm now going to go into the particular methods and techniques that we use to achieve our result. The main idea in our work is to use purely functional trees, which are a textbook data structure. You can find them, for example, in the SICP book. You're storing an ordered set of elements according to some sort of balancing criteria, for example, red-black or weight balance. How do we represent a graph using a purely functional tree? It's a simple idea. We have a tree of vertices storing the vertex IDs, and every vertex in the vertex tree, each node in this vertex tree, stores a purely functional tree of its edge IDs. So it's a two-level purely functional data structure consisting of a purely functional tree on the vertices, and then every node in this vertex tree has associated with it a purely functional tree storing its adjacency information, its incident edges. Now, there are several desirable properties about using purely functional data structures to solve this problem. The first is that we can use well-known techniques like path copying to generate new versions of the data structure. So for example, if we want to insert an element into a purely functional tree, it's very easy to do this. We just create a new root. We basically create a new node for the updated side, and all of the elements that are not updated by the update are just pointed back to. So if you have a tree with n elements, it's easy to see that in log n work and log n space, you can generate a new version of this tree with an element that's been inserted or deleted. And in fact, this style of update algorithm actually generalizes to handle batches of updates in low work and depth. And to define these terms, the work is like a notion of sequential time in the parallel setting, which is the total number of operations you do, and the depth is the longest sequential chain of dependencies, or the critical path length of the parallel computation. So our colleagues have developed very nice work showing how to process batch updates in parallel with nearly linear work and polylogarithmic depth. So these kind of algorithms get great speed up. In addition, using purely functional trees guarantees immutability. Every purely functional tree is an immutable snapshot, and so when we store a graph as a purely functional tree, we get an immutable snapshot of the graph. Now, this is desirable in a graph streaming system because we can essentially store a pointer to the latest version or the latest snapshot of this graph. So in this example, all of the nodes are reference counted, and this pointer has a reference count of 1 to this root of this tree. So when a query arrives, it can read this latest version of the pointer and atomically try to acquire a handle to this graph snapshot. And once it acquires the handle, it starts running its query. Now, in the meantime, concurrently with this query, the updater could arrive and create a new copy of the graph in response to some updates. And notice that these updates are completely independent of the previous snapshot. The query running on the previous snapshot is completely oblivious to this update. Finally, once the update is done, it can swing this latest version pointer to point to the new graph, and that decrements the reference count and bumps the reference count on the new version. Now, when a new query arrives, it can go and start running on the new version of the graph. And finally, once the old query is finished, it can decrement the reference count, and by recursively decrementing the reference count on the nodes, we can eagerly garbage collect and free all the memory that's not used by the system any further. And I should note that this approach was proposed in a very recent SPA paper by our colleagues in SPA 2019, which I recommend you read if you're interested. However, it's not entirely a bed of roses. There are some disadvantages to using this naive proposal as I've outlined so far. The first is that if we represented graphs using just purely functional trees in this way, we would suffer very poor cache performance. Because we're storing a single tree node per edge, on a graph with a few 100 billion edges, we're going to suffer basically a single cache miss per edge. And that's going to cause a significant performance hit. In addition, as you might guess, storing a single tree node per edge would cause a huge amount of space to be wasted. So if we're using 32 bytes per edge node, this is going to, again, require a few terabytes of memory to represent a graph with a couple of hundred billion edges. And so to drive that point home, it would require close to 7 terabytes of memory to store the hyperlink 2012 graph, which has 225 billion edges. So I want to compare the space usage with the best. In this slide, I'm going to show you the space usage of using purely functional trees with the space usage using Ligro+, which is a state-of-the-art static graph processing framework that represents graphs using integer compression. So that's the yellow line outlined here. And you can see that we can represent the hyperlink 2012 graph using just 350 gigabytes of memory. On the other hand, representing them using purely functional trees requires 6.8 terabytes of memory, which is a 19.6x overhead in space. And so it becomes quite unfeasible to represent this graph on a single machine unless you're willing to spend a lot of money on RAM. So it's an interesting question whether we can actually improve the space usage and the cache performance of this approach using purely functional trees while preserving the other desirable properties of purely functional trees, namely being able to generate new versions using path copying and the immutability properties which enable concurrency. So we solved this problem by designing a purely functional compressed tree data structure. It's a very intuitive idea, and the idea is that instead of storing elements in different tree nodes, every element in a separate tree node, we're going to try to chunk together the elements so that multiple elements are stored inside the same tree node. So the data structure takes as input a parameter b, a chunking parameter b, and at the start of the system, we fix a hash function h. And the idea is to subsample a subset of the elements to be heads, with probability 1 over b under this hash function. So given a purely functional tree like you see here, we subsample a set of them to be heads with probability 1 over b. Those are the yellow elements marked here. And from these heads, we generate a new purely functional compressed data structure as follows. So we generate a tree on the heads where all of the elements that are not heads that come after a head in the sorted sequence of elements are associated with that head. So these elements that are not heads come up as tails. And so you have a subarray of tails that are associated with the first head that appears before them. And so the purely functional data structure is now a purely functional tree on these heads where the values are these chunks. And notice that there might be a collection of tails that don't have a previous head associated with them. So we call this the prefix, and the C-tree data structure is the combination, this pair of a prefix and the purely functional tree on the heads with these chunks as the values. Now notice that if we set this b parameter to be the size of a cache line, we can now store the expected size of these chunks is going to be a cache line. So if you're storing integers, you would set this b to be like the size of a cache line by 4, and you would get roughly a cache line worth of integers inside of each chunk in expectation. In addition, we can further improve the space usage of this approach by, in the case of integer C-trees, by using difference encoding. Because we're storing sorted integers inside of each chunk, we can store the differences, which are going to be usually much smaller than the raw integers themselves, and reduce the space usage down to maybe a byte or 2 bytes per integer. We designed a number of tree primitives using C-trees. Unfortunately, I don't have time to tell you about them today, but they all have good theoretical bounds in their work and depth. For example, C-trees support sequential insertions and deletions, and also batch insertions and deletions with good work and depth. But please see our paper for these details. Now, if you remember, this was the space usage using purely functional trees, this blue line here. So the moment we replace the edge trees in our system from purely functional trees to C-trees, we achieve the space usage seen in the green line here. So I just want to draw your attention to the fact that we can now store the hyperlink 2012 graph using about 700 gigabytes of memory, which is well within the space usage of our 1 terabyte machine. And so now we can store this hyperlink 2012 graph on our machine and actually run analytics on it. And this represents a 9x improvement in the space utilization compared to purely functional trees. In addition to designing C-trees, we integrated them as part of a graph streaming framework that we called Aspen, as I mentioned. And Aspen is an extension of the Ligra graph processing framework with primitives for updating graphs. We basically introduced the following primitives for maintaining a graph that's being updated in response to new updates. And so we assume the updates are processed by a single writer, which can internally be parallel. And it provides primitives for concurrent readers to acquire a recent snapshot of the graph. So the readers call acquire to acquire the snapshot and call release to free their handle to this snapshot. And there are primitives for inserting batches of edges and deleting batches of edges, and similarly for vertices. And so Aspen builds on our prior work from Ligra and from Julienne, which introduced primitives for static graph algorithms. I'm going to now switch gears and tell you about our experiments. We ran our experiments on a Dell PowerEdge R930 machine, which is a 72-core machine that's two-way hyper-threaded. It's equipped with a terabyte of main memory, and most of the cost of the machine actually goes into buying this memory. And we support parallelism by using a custom designed work stealing scheduler that's designed similarly to Silk. If you want to actually buy one of these machines, it'll set you back about the price of a new Nissan Leaf. It's about $30,000. So if you're wondering what to ask your spouse for Christmas, maybe this year, you could ask them for a fast shared memory multi-core. And if you're unlucky and this doesn't work out, I should note that you can rent very similar machines on the cloud today. So by paying 20 or 30 bucks an hour, you can rent a similarly equipped machine with a large amount of RAM. We ran a number of experiments in our paper, but I'm only going to have time to tell you about one of them or two of them today. And the main question I want to address is, what is the latency of performing single edge updates that are run concurrently with queries? So for this experiment, we generated an update stream consisting of a mix of edge insertions and deletions. And we sequentially ran this update stream. So we had a single writer that's inserting these edges one at a time into a graph. And alongside this, there's a sequential stream of BFSs that are breadth first searches that are being run one at a time. Now, the updates are being run on a single hyperthread, and the BFSs are internally parallel and run across on 143 hyperthreads. And when we ran this experiment that when we were running these updates and queries concurrently, we can make a single edge update visible in less than 100 microseconds across all of our graphs, including this hyperlink 2012 graph with over 200 billion edges. Now you might ask, what is the effect of running these updates concurrent with the queries on the query latency? So we ran an experiment where we ran the queries in isolation using all 144 hyperthreads, and then run concurrently with the updates using 143 hyperthreads. And we found that there's less than a 3% impact on the queries in this concurrent setting, which might be due to having one fewer hyperthread. In addition to running this single update experiment, we also measured the performance of our data structure when processing large batches of updates in parallel. And the green line shows our update throughput in terms of edges updated per second versus batch size. And we compared our throughput results with Stinger, which is a state-of-the-art shared memory graph streaming system that's available today. And we found that we're, in the worst case, 32x better, which is already an order of magnitude better throughput, and in the best case, 329x better throughput than Stinger. And this is because Stinger is unable to achieve throughput rates higher than about 300,000 per second and cannot scale to large batches. And there's many other experiments that were not, unfortunately not included in this talk, but please see our paper for these details and our experiments. So I wanted to address this main question in this talk today, which is whether we can design a graph streaming system that can efficiently represent, analyze, and update the hyperlink 2012 graph and other graphs at this scale with very low latency on a single machine. I hope I've convinced you in this talk that the answer is yes. You can do it using Aspen. And we've made all of our code publicly available, so you can find it on this GitHub link here. And I should acknowledge many of the prior papers that our work has been built on, and the work really would not have been possible without this prior work. So I'd like to thank them. And that's it. Thank you.
Really
chat after.
Really cool talk. Thank you. So you mentioned that the heads in these C trees are selected randomly, and I assume that's to protect against some worst case behavior. So
okay, it's a great question.
What do those worst case instances look like, or what is it you're trying to avoid there?
You could imagine if you tried to design a deterministic chunking scheme where you started off with a set of elements and you deterministically pick things at a stride of B. Mm-hmm. Now an adversary that knows this could basically delete all of the elements and make these chunks much less full. Mm-hmm. And so you'd have to design some rebalancing schemes that merged unfull blocks. And we didn't want to deal with that, so we designed this randomized scheme which just works well in expectation.
Makes sense.
But designing a deterministic scheme is an interesting problem.
Thanks.
Thanks.
Okay. Let's thank Lexman again. Okay.